video, I'm going to take you through electrons and bonding, and I'm going to share my screen. And here we go. Now, if you were in class, you could, I'd ask you to go through some of these sort of recapping sort of ideas. So you could stop the video now and have a go at them. Okay, right, so here are the answers. Okay, so that was a bit quick. There you go. You could again stop the video if you would like to check the answers. Okay, so here's our basic page. Remember that we do have support sessions on Mondays and Tuesdays. Okay, now please try and complete chapter page 16 in your book. This will help with revision chapter 2. Here is the task here. Okay, so you're trying to write down the formulas of these ionic compounds. So you could now stop the video and carry on when you are ready. Okay, so here are the answers. I'll put those all up, and again, you could stop the video and check it now. Okay, so here in your booklet, this is on page 13 of your booklet, you are going to try and figure out what type of chemical bond exists in the different types of compounds that are listed below. And once you've done that, you need to state whether each compound has a high or low melting point and whether they can conduct electricity. So again, you can stop the video. And when you've had a go and done it, you can carry on. Okay, so here is the answers. Okay, and again, oops, I'll get back a minute. We should be able to stop the video now. Okay, and then you could check your answers. Right. Okay, so electrons and bonding. Okay, so these are the objectives. Okay, so we're going to look at ionic bonding and calling it electrostatic attraction between opposite charged ions. We'll hopefully be able to do dot and cross diagrams, okay, and look at giant ionic lattices, and then we'll be considering the properties. Okay, so those are our keywords, okay, there's a rather interesting or rather facile pun there about the group 1 metals and the group 7 non-metals, the halogens. Okay, so those are the definitions. They're in your booklet, so you need to make flashcards of those. Okay, so the types of bonding. Atoms can be joined in 3 possible ways: metal and non-metal, which is going to give us ionic bonding. Okay, non-metals only will give us covalent bonding, and if we have metals only, we have metallic bonding. Okay, all 3 are going to involve the outermost electron shells of the atoms, and we can actually think of it as the Bohr model rather than the SPDF, although later we will be writing out SPDF for the electrons to see what happens. Okay, so species that ionically bond, metal and non-metal. Okay, what does the metal want to do to become stable? Yes, it wants to lose electrons. Okay, it becomes positive, and for example, there's magnesium. Okay, it's group 2, so this is 2 electrons. Non-metal it wants to gain electrons. It's closer to being full, so it's easier to gain electrons than to lose them, so it becomes negative. It's got more electrons than protons, so it's a negative. E.g., chlorine there is only 1 electron away from having a full outer shell, so it gains 1 and becomes negative. So once they have done that, once they've given each other their electrons or swapped their electrons, then we have electrostatic attraction. It's electrostatic because it's the electrons are being transferred, and it's static because the charge is stuck to that species. It's stuck to the chlorine, or it's stuck to the magnesium. Okay, and then they're going to stick together. So how do you know the charge on the ion? Well, use the position in the periodic table and the electron configuration, and you work out how many it must lose or gain to become the same structure as a noble gas. That's the simplest form of it. That works well with the group 1s and group 2 metals, and it works well with groups 5, 6, and 7 of the non-metals, but not so good with transition metals, which we'll talk about later. Okay, so opposites attract, and therefore we end up with an ionic crystalline structure that could look something like this: positives and negatives sticking together. Okay, and it will go on and ion and ion. Okay, so now that's, you know, a simple structure, which is like one layer of atoms, but this is going to make a 3D shape, and so we end up having a giant 3D ionic lattice. So ionic substances form giant ionic lattices with millions and billions of ions in them. Okay, so here is a summary. Okay, so you can stop the video now and have a go at filling in the gaps. Should be fairly quick, and when you've done, you can carry on. Okay, so here are the answers. You can check those. Okay, and then carry on. Okay, now obviously you may people have had varying teaching in GCSE, so you should be able to have a go at dot and cross diagrams. Try question 8 in the booklet on page 15. So hopefully most of you will be able to draw the majority of those dot and cross diagrams that are in the booklet. You might be able to help somebody else do it. And what I'm now going to do is I'm going to go through some of the more complicated ones. Okay, so you could theoretically just stop the video and carry on and just work through it. Okay, and then you can just speed through some of this video if you need to. Okay, so metals are going to lose electrons. The number is going to be usually equal to their group number. So magnesium is in group 2, loses 2. Lithium is in group 1, it's going to lose 1. Okay, yeah, so there's aluminium. It would lose those 3 on the outside, okay, to become Al3+. And you can see they've got a new electronic configuration. This is their original electronic configuration, okay, and so they would lose that. Lithium would become 1s2, magnesium become 1s2, 2s2, 2p6, and aluminium would be 1s2, 2s2, 2p6, 3s, 2p6. Okay, it will lose those 3 electrons there. Although later you'll find that aluminium is a bit special sometimes. Okay, so the non-metals, so oxygen is got 2p4 at the end, it needs to gain 2 to become 2p6 and have a full shell. Chlorine is to gain 1 to become 3p6 to gain 1 shell, to gain 1 electron. Okay, so once it gains those 2 electrons, once oxygen gains those 2 electrons, it becomes 2p6 and it's 2 minus, and chlorine is 3p6 and is 1 minus. Okay, so sodium ions. Okay, here's our sodium atom, loses the electron. And then now this is where we have to be very careful and make sure we don't mix up the diagrams. This is an ionic diagram with electron shells, dot and cross diagram. We have drawn it and we put it in a square brackets or set of square brackets and put the positive sign outside. It's lost an electron to become +1. Okay, so it now has 2, 2 and 6, i.e. 10 electrons, but it has 11 protons in the center, so it's +1. Ions must be drawn with square brackets around them, okay, and they're not overlapping. Now you could get away with us actually just drawing the outer shell, so just draw this one here, and obviously put sodium as a symbol in the middle. Okay, but it needs something that can actually take hold of that extra electron. So chlorine has got 7 electrons out of shell. It can gain an electron. That's quite good because sodium wants to lose 1 and chlorine wants to gain 1. So it will gain 1 electron from the sodium to form a Cl- ion. Again, it's now drawn in brackets with the minus sign, and we've got the extra electron from the sodium. Okay, so therefore we would form sodium chloride. So that electron has gone to the chlorine. Okay, and we end up like that. And you need to draw it like that. It must be separate. Okay, with square boxes around it, and positive. And again, we don't necessarily need to draw the inner rings, just the outer shells. Okay, so we can assume that the inner ones are full, so we can just do that. Yeah. Okay, there we go. Oh, yeah, so that's equally acceptable. Yeah, and notice with the sodium, we've actually just drawn the outer shell as empty because it's lost its electron. The inner ones must be full. So magnesium oxide, okay, so magnesium oxide is taking it a step higher. We've got magnesium wants to get rid of 2 electrons, oxygen wants to gain 2, that works nicely. Okay, so we end up in magnesium oxide, okay, and each of the ions now has a full outer shells. The P ends in 6, the P ends in 6, so we've got full outer shell of 8, S2, P6 equals 8. Okay, again, we can simplify that. There we go. Okay, so now what about sodium fluoride? This is for you to go at, so you can stop the video now, enjoy yourself. Okay, so that's going to look like this. Okay, lithium oxide. Now, in this case, oxygen wants to gain 2 electrons, but lithium's only got 1 to give, so we need 2 lithiums. Hence, it's Li2 is its actual formula. Okay, so we've got to aluminium fluoride. Okay, so with the aluminium fluoride, aluminium needs to get rid of 3 electrons, and the fluoride needs only 1, so we need 3 fluorines. And so those works like this. Okay, so having seen that, okay, now have a go at working out magnesium and fluorine, what happens when they get together, and aluminium and nitrogen. Okay, so stop the video now, and then carry on once you have drawn those out. Okay, so, okay, there is a quick quiz now that you could do. So here they are. So have a go at these now, which of the following will have ionic bonding. Okay, and the answers will come at the end. Or no, they'll come now. Okay, so right, which is not true. Okay, not two-dimensional, it's 3D, goes on for big dimensions. What's true about the oxide ion? 2 minus charge. Okay, so I'll just go through these. Okay, so now we move on to dry-organic lattice. So we have this lattice. Here is a crystal. This could be sodium chloride, for instance, and the green one would be the chlorine. Because just think about it, an ion, if it gains an electron, it's going to get bigger. And if it loses an electron, it's going to get smaller. So the positive ones tend to be smaller than their atoms, and the negative ones tend to be bigger than will be bigger than their atoms. Okay, so the negative one's bigger than their atoms, positive one's smaller. So then we have this is what a crystal lattice is, and it depends what the arrangement of that crystal lattice depends on the relative size of the ions. Okay, so that's sodium chloride. Sodium ion is small enough relative to chloride ion to fit in the spaces, so you have both ions on every plane. Okay, so they can fit together nicely. So if you look at one sodium ion in particular, put it in the middle of the cube, it is in contact with 6 other chloride ions. Okay, so its coordination number is 6. Okay, and if you look at chloride, it's again surrounded by 6 sodium, so its coordination number is also 6. Okay, you can see that with that arrangement there. So this sodium ion is in the next cube, next part of the lattice. Moving on. Okay, so the physical properties were going to be very high. A large amount of energy needs to overcome this strong electrostatic attraction. Now, the thing is they're brittle. They're not like metals, they're brittle, okay, because a dislocation, that means just sliding past each other. Then the repulsion will split the crystal, because if you slide the crystal, you're going to put a sodium next to a sodium or a chlorine next to chlorine, and they'll repel each other. They're not going to conduct. The ions are not free to move. They will conduct, though, when they are molten, and it's the ions that are moving, not electrons. Okay, so ions become mobile. So an ionic solid, it's not electrons that are moving, it's the ions that move. Soluble, they're not soluble in non-polar solvents, but they are soluble in water. Okay, water's a polar solvent, so water's got oxygen, which is what we'd call an electronegative atom. It pulls electrons towards it more than the hydrogen does, so it's what we call polar. Okay, and ions or ionic substances will dissolve in that. So the melting point's high. Okay, strong electrostatic attraction. Which is going to be higher though, calcium oxide or sodium fluoride? Okay, so you need to think about what the ions are. So calcium is 2 plus, oxygen is 2 minus, sodium is plus, and fluorine is minus. Calcium oxide will have a high melting point because there's more electrostatic charge. I've got a greater charge and greater attraction. Whoops. Okay, so here this is explaining why they're brittle. Okay, here that's fine. The ions are lined up, negative to positive, negative to positive. But if you push it or twist it or try and move the ionic solid, you're going to push the negatives next to negatives and positive next to positives. It breaks up. Now in class, you will do this demo where we'll actually look at seeing how ionic substances conduct. And they conduct because once they're molten, the ions are not stuck to each other and they can move around. And they can move to electrodes. And solutions will also conduct. So molten and solution will conduct. Okay, so in a solid, the ions are fixed and lattice and can't move. If they're molten or aqueous, they then can move. Okay, so this is the water. Now, this is what we mean about water being polar molecule. The oxygen attracts the negatives towards it, so it's not fully negative, or the hydrogen's not fully positive. But we have this little symbol here, which is the delta, the Greek letter delta, which is a small lowercase delta, which means slight or partial. So the oxygen is partially negative and the hydrogen is partially positive. And that you can see the water molecules get in there and they start to get attracted towards the ions in the crystal structure, and they will then pull it apart. And then we have hydrated cations or hydrated anions, cation being a positive one, anion being a negative one. Okay, so, but there's lots of water molecules, so it does require a lot of energy, but the water molecules have got that. And they're now stable because they're surrounded by water molecules. Okay, so here is a gap fill for solubility. So if we stop it, you can have a go at doing that now. Okay, so let's have a look at the answers. So let's pop the answers in. Check your answers, so you can stop and check. Okay. Right, so here's an example exam question. Magnesium fluoride has ionic bonding. How does ionic bonding hold particles in MgF together? Okay, so let's have a quick look at the answer. So the answer is electrostatic attraction between oppositely charged ions. So where are the two marks? Electrostatic attraction, 1. Oppositely charged ions, 2 marks. Okay, second question. Draw a dot and cross diagram for magnesium fluoride. Show outer electrons only. Okay, so the answer, so here, correct dot and cross diagram with correct charges. Okay, so we're going to do magnesium fluoride. Okay, so its outer electrons have been given away, but it needs to give it away to 2 fluorines. So the fluorine, okay, so 1, 2, 3, 4, 5, 6, 7. Okay, and I'm going to use a cross for the magnesium's electron. So this is fluorine, okay, and we can put that. The magnesium is 2 plus, the fluorine is -1, okay. So I'm going to need another fluorine. I could draw it like this. 2, 3, 4, 5, 6, 7, and 8. Okay, so that's negative. So I could draw it like that, or I could just a big 2 in front of that, okay, which shows I've now got 2 fluorines for every one magnesium. So correct dot and cross diagram, correct charges. Okay, and then the last question was, a student found that magnesium fluoride has different electrical conductivities when solid and when dissolved in water. Explain 2 observations. So when it's solid, the ions cannot move, so it cannot conduct. They're in fixed positions. In solution, the ions are free to move and mobile, so it can conduct in solution, but not solid. Okay, so that's it. There are some things to have a go at. Okay, so you can work through those. If you stop the video now, you can work through that stuff. So here are the answers to the booklet questions. Okay, and this is the mark scheme. So things like, ignore. So sometimes I'll write on your answer sheet IGN, which means ignore. Sometimes you know, here when it's talking about how do ionic substances conduct electricity when they're in solution or when they're molten. Okay, if you say that the electrons moving, that is a con. Okay, which means it's would take a mark off. Yeah, so is, you know, it's not, and sometimes you might get con written on there. Or is a marking word. So that means you can have either or those things. Sometimes the mark scheme will say and that means you have to have both statements to make to answer the question correctly. Okay, so that's those, and you can stop the video to check that question. Okay, going further with the questions. Okay, question 2. So again, if you want to check that, you would obviously stop the video and check that. Okay, and so that's what we've covered today.